Hello everyone, hope you're all having a great time. Welcome to this YouTube channel, and in this tutorial we're going to have a comprehensive study on the integration of renewable energies in order to supply the demand of an absorption chiller system. So basically this tutorial will cover most things such as the linkages between the components, a study case on each of the components as well, for instance the PV panels that are intact, as well as the electrolyzers and the fuel cells that are being used for this problem. And we're going to model this together and simulate it using the TRNSYS software. So stay tuned, guys, as we continue with each step. As an overview, I'd like to first talk about what is the steps that are going to be taken in this problem-solving project. So first of all, I'm just going to talk about the problem that I'm going to discuss about. Now, this problem is depending on my situation, but it could change for yours. And then we're going to have a basic study on each of the components, the linkages, and everything that has to be known in order to pretty much link and set up all the devices and integrate them into a cycle, let's say. And we're going to have the modeling of the system, as well as the simulation using the TRNSYS software. So it's important to understand what is the main feature and key of this project. So moving on, let's talk about the problem. See, I'm just going to read out this major problem that we have, which is important to understand first. And then depending on each of the parameters that are going to be defined, we're going to assess the cycle. So the goal is to design a renewable energy system where solar panels generate electricity to power an electrolyzer that produces 5 kilograms of hydrogen per day at 7 bars. The hydrogen is then compressed and stored in a tank at 200 bars. Later, the stored hydrogen is supplied to a fuel cell to generate electricity for the running of a 2-ton capacity absorption chiller system. The challenge is to determine the number of panels required and ensure that the entire system balances in terms of energy and hydrogen demand. So we're going to discuss about this. Don't worry at all. It might sound hard and difficult, but it's not. So the main concept is pretty, straightforward. So we're just going to use an array of solar panels to provide the required electricity to power up the electrolyzer that can produce 5 kilograms of hydrogen in one day at 7 bars, which is a defined parameter. So don't worry about that. First, we're going to work our way through the solar panel first. And the linkages are pretty straightforward. So you can see that we have an array of PV panels. We're going to connect that to the electrolyzer. The type will be also discussed further ahead. And then we're going to use a storage tank to pretty much store the amount of hydrogen that we have produced using the electrolyzer. And depending on the need of hydrogen, we're going to then supply it to our fuel cell. Now then this fuel cell can provide electricity, and the required amount of electricity, which is about 14 kilowatts, which is equivalent to 2 tons of refrigeration as a capacity to supply the need of an absorption chiller system. So let's move on with each of the components first, have a basic concept study, and then we will bring all these together. So moving on to the modeling of PV panels. Now, every solar panel that you buy, if you want to integrate them in an on-grid or off-grid application use, they come with a catalog. Now these catalogs define some parameters, the manufacturer, the place that it has been produced, and many other things. Now they have different values for each of the parameters that are being discussed. For instance, the voltage, the current, the efficiency that each module has. There are coefficients that relate to temperature. For instance, ISC, VOC, or Pmax. And each panel that you buy in their catalog, they come with this IV curve and PV curve. which tends to show how the current change with the voltage of the array and the module. So as an analysis review, I chose an arbitrary region depending on my problem, which I chose San Francisco in the United States of America. And then I want to just have this basic study on how the effect of solar intensity radiation will have on the power of the arrays. The fixed and constrained number of modules that are used in parallel is 10. It's fixed. The thing that we have to pretty much change and play with is choosing the right number of panels in series. So it's important to define this panels in series depending on your problem. For this problem that I've chosen, I'm going to discuss what will the number be. But for your problem, you have to see how things might change and what is the right number of the panels that you're choosing in series. So let's move on to the next part, which is going to be the modeling of PV panels in the TRNSYS software. Okay, so here we have the workspace for our TRNSYS software. The first thing that we're going to do is we're going to create a new project. I'm just going to click on this empty project and you're going to maximize this. So this is going to be our workspace, and everything is going to be imported to this section from these libraries that we have in the components that are stored in them. So the first thing that we want to do is that we want to add our weather data. So I'm going to use the standard format with TMY2, and I'm going to import this. There are other ways as well to import your weather data depending on your region. But you're going to come to this like external part. You don't want to do anything with these parameters or outputs. And you just want to open this external file. And you're seeing it's by default in Wisconsin, Madison. So we're going to change this to San Francisco. You're just going to press on Browse. And then you're going to pick San Francisco for your weather data out here. So I've chosen this, but I don't want to do anything right now with this because it's not in a necessary state for right now. But what we're going to do here is we're going to come to this electrical part because we want to add our photovoltaic panels. Now there are other types such as advanced models and basic models. The advanced one has an inverter included in it. You can see like with no MPPT, it's no inverter, or with inverter. We're not going to do select that. We're going to just go to the basic model with no MPPT, and we're going to import our solar panel. Now there's some important parameters that have to be added to this. For instance, we're gonna pretty much change the default settings depending on our problem. So the one that I chose, before that, I have to tell you that the catalog will mention all the things that I have said in the previous section as well. So the short circuit current is going to be at 14.4 amperes. The open circuit voltage will be changed to 39.1 volts, and you're not going to do anything with the reference cell temperature or the reference insulation. But for the module voltage at max power, you're going to change that to 32.65. And for the module current at max power, you're going to change that to 13.63. And as mentioned, you have to also change these coefficients of ISC or VOC as well. So it's going to be 0.045 and negative 0.25. And two other main factors that have to change, could change, are the module area, the number of modules in series, and the number of modules in parallel. For now, we're not going to change this, although we mentioned that the number of modules in parallel have to be 10. But for now, we're just going to keep that. Coming to the input section, now the weather data has all the required values for the beam radiation, sky diffuse radiation. But right now, because we want to just plot the PV curve and IV curve, it's best for us to only change the load voltage. It could either be 25 volts or 30 volts. And I'm going to also change this beam radiation. We're going to see what the beam radiation has as an effect on the power. So first of all, I'm just going to change it to 600. Now, I'm going to change the unit as well. It doesn't make that much difference, but I just wanted to make it more sensible. So let's just change it to 600 watts per meter squared. And with this part, I don't want to interfere anything else into this part, because then I'm going to show you what fluctuations it would cause. So I'm just going to keep these at this state. I'm going to close this. Now, I would want to use an equation. Now, why am I using such thing in order to plot the PV curve and IV curve? So if you take a look at this equation, you can add an output for it. Let's say it's voltage as the preferred name for it. And I'm going to include time divided by 100, because TRNSYS is a transient software, and it's based upon time. Now, the voltage that you're defining for it changes with time. You want to do that, right? So you're pretty much changing the voltage with time divided by 100. And I'm going to link this to my PV panel. I'm going to link the voltage with the load voltage. So the load voltage will start from 25 volts and it will decrease gradually. And for the appearance of the linkages, you can define the best position in order to have a good linkage, but we're not going to worry about that for now. The next thing that I would like to do is I would like to go to the output section, use an online plotter without file, and add this here. Now, as you can see, if I link this together, I want to extract two things, the array current and the array power. I'm going to plot that. So I'm going to choose the left axis for the power and the right axis for the current. So I want to plot the IV curve as it is. And let's make some changes in here. I think 1,000 is a lot, so I'm going to put it to 400, for instance. And for the right axis, the current should be at a lower than 50. So let's put it at 40, for instance. And now I'm going to run this and see how things change. So you're seeing that there's not a good gap, because the time that it's seen is 168 hours. So we're going to do something. We're going to come to the settings section. It's based on 8 days. So we're going to change this 168 to 8,760 hours, which is a total year. So it's from the 1st of January till the end of the year, which is the 31st of September. And we're going to change our time steps to 1, right? And now we can plot this and run this and see how things change. Yeah, that's the change that we are demanding. Now, it's really important to see what axis you're using on the right side. So let's change the background and the thickness of the lines. And you can see we're seeing that this is the IV curve and this is related to the PV curve. Now, in order to make it a bit neat, let's change this 40 to let's say 20, or let's say 30, right? So as you can see, this is way better. It's changed a lot. Now, as I mentioned, this is also the difference that it makes. If I change this beam radiation, look how much it would change. So I would change it from 600 to 800. And you're seeing that if I run this, yeah, you would see this huge gap that is created here, because you're seeing the first time it was about to this region and now it has increased. So the beam radiation defines pretty much that you're increasing the power on the surface of your modular array of panels. And if I change this to other values from 900, you would see the change as well. So I've also included, pretty much you can see it's way up there, so it's above 400 watts. And this is not temperature, so you could change this as well. I could change it to, let's say, power for the left axis, which is watts, and the right axis would change to current, which is pretty much in amperes. So as you can see, we've seen this delicate change. I'm going to also put this, like for instance, to 500, change it to 500 and see how things are. And you can see that the IV curve and PV curve has been depicted here. And also I have listed this plotting for the PV curve in 3 different beam radiations, which are 600, 800, and 900 watts over meters squared. So now that you have plotted this IV curve and PV curve for your solar panel, you can now add, for instance, your weather data. If I add the dry bulb temperature to the ambient temperature, see what happens. You would see that you're seeing a fluctuation, and this is due to the rate of temperature being different in every day throughout the year. So that's why you're seeing these fluctuations, right? And as you can see, the time limit is also till 4,000. So if I change this from 8,760 to like 4,000, you're able to see the difference that makes. And this is due to something, because the voltage is 25 volts and you're gradually decreasing it, and this voltage will decrease to a certain level until it reaches 0. So now that we have chosen the right thing, I'm going to keep this here, but now we want to enter the next zone, which is pretty much integrating the solar panel with the electrolyzer. But first, we would like to know that what is the total power extracted from one solar panel, I mean like one module in series and one module in parallel state. So you want to add something known as an integrator, which is a quantity integrator, which what it does is that it pretty much sums up the value of anything that you want throughout the year. So we want to link the power to that, and then I'm going to use something as a printer, an unformatted printer, to see what is the final value in 1 year. So we're going to see like how much power does one solar panel produce. So I'm going to connect this here. I'm going to connect it as well to this region. And now we would like to run this. So let this software run. And one thing that you want to change as well, which would help a lot, is for instance, right now we don't need to enter the weather data. We're going to worry about that later. So I'm just going to pretty much run this again. And seeing from the changes, you're going to open this printer, you go to the external file, edit, just going to press OK on all of these. And this will show you one important thing, that from time and the result is the power in watts. And the time is from 0 to 8,760, which is 1 complete year. And you'd see that you're producing this much power with one solar panel. And it's pretty much a good number, but it really depends on how your modules are set in parallel and series. So now that we have understood most part, you can also try to see what would the power be if you added the solar panel and linked it with your weather data. So I'm just gonna delete these components right now. I think we don't need them at all right now. So I'm just going to keep this here. And now we want to add the linkage between the weather data of San Francisco and the solar panel. So I'm going to add the dry bulb temperature to I'm going to link it to the ambient temperature. For the beam radiation, I'm going to also connected to this, but this will change. It will be set due to the weather data out here. The sky diffuse radiation will change this part. The ground reflected diffuse radiation for the surface will be linked to this. The slope of surface will be to the array slope, and the angle of incidence for surface will be linked to this. And the low voltage will be set to 25 for us for now. And now let's see what happens. So if I plot this, you see that you're seeing a good change. Now the red lines, you would see they're fluctuating because it's due to the transient state that this software has. And this will be the power that it is providing. So it's obvious that during the summer and let's say end of the spring, you're witnessing a fairly high amount of power being extracted from that panel. So this is the basic case for the initial part of the study. But now it's time for us to integrate this solar panel to the electrolyzer. And one thing that you want to change right now is we're going to set this to 10. And next, we're going to see what should we do, what should we change with this number of modules in series in order to produce 5 kilograms of hydrogen using the electrolyzer. So we're going to stay tuned with that and see how things proceed. So now moving to the electrolyzer, after we have assessed pretty much most of the information that was required for our PV panels and their distribution, it's now time to move to the next component or the next linkage. So the next linkage would be an electrolyzer. The type of electrolyzer that I've used, there are numerous amounts of electrolyzers out there, but the one that I chose was the alkaline. And as you can see on the left hand side of the page, you're able to see the polarization curve for such electrolyzer. And you're seeing this blue line, which says the electrolyzer performance. And it increases, it gradually increases from 0 to, for instance, let's say 6. And this is due to the losses that are in front of the performance of the electrolyzer. Now, these losses could be activation loss, which is usually known as region 1, the ohmic loss, and the concentration or mass transport loss. So these losses do actually affect the performance of the electrolyzer, not letting it have a good efficiency for us. And there are lots of ways that you could reduce these losses, which will not be mentioned here. But now we're going to use this type of electrolyzer with these parameters defined. For instance, a max current density of 1000 milliamperes over centimeter square. And actually, in this part, you have to pretty much constrain the number of electrolyzers in series in parallel, which I've chosen 3 for the parallel and 20 for the series. So now I think, depending on this, I'm going to talk about that more in the TRNSYS section. How should we link these PV panels? What do they need in middle of them? We're going to discuss that more further ahead. So now that we have the weather data and the PV panels data in hand, we want to proceed forward in order to produce 5 kilograms of hydrogen in one day based on an average scale in San Francisco. So in order to do that, we would like to produce this hydrogen using an electrolyzer. So you want to come to this hydrogen systems, and you want to click on the electrolyzer and drag this electrolyzer to this state. And what you want to do right now is to define a few of the parameters that have been discussed previously. So for the electrode area, I chose 0.03 meters squared. The number of cells have been determined previously, which we will change it to 20 in series and 3 in parallel. And the maximum allowable current density is 1000 milliamperes over centimeters squared. But for the other things, you don't want to change in the parameters section. Now you want to head to the input area. And you would see that there are a few variables that could change, but we will not do anything with those. But two values that you should remember is the electrolyzer pressure, which is 7 bars, and the electrolyzer operating temperature, which is 50 degrees Celsius. So the reason why we chose this is pretty obvious. It's a default side, and we, as we mentioned in the stating of the problem, we said that we want to produce 5 kilograms of hydrogen per day in 7 bars. So that's why we use this number. So anyway, now let's proceed into adding a mediator in order to control the power output from the solar panel to the electrolyzer. We're able to do that with an controller, a master controller for the electrolyzer. You don't want to use the master controller because it includes features such as fuel cells and a diesel backup power. But right now we're just using electrolyzer, and you want to choose the variable power mode. So we're going to import that here. I want to create this linkage between the PV panel and your master controller, and you want to link the array power to the power to electrolyzer. So this is what you're going to do first, right? And what you want to change is this idling power is too much. You want to change that to 1000 and let's say 700 watts. Anything between 1500 to 1800 is fine for this problem. Now, because this example is based on a power conditioning state, you want to add a power conditioning with an input power being known. So you want to use this tool here, and you want to connect this master controller to your power conditioner. And you're going to link these two together. And what you want to change from here, this is the nominal power. The nominal power is high, so you want to decrease that to about, like, let's say 12,000, 10,000, 12,000. It's up to you. And what you want to do next is you want to make this look pretty fine. You want to add a state where you could create this linkage for your power conditioner to your electrolyzer, and you're going to do that by first linking the output current. So it will read the output current, and it's in amperes for both sides, so it's good. We don't have any problem with this. And then you want to have this electrolyzer send back the signal of the voltage that has been taken into measurement. So you're going to do this. And we could also change the name. So I'm going to change this to MC, this one to PC for power conditioning, and this one is the AEL, the alkaline electrolyzer. So in order to have a good, understanding of how things are, we want to see how much hydrogen is produced. But in order to produce 5 kilograms of hydrogen, let's first use, so I'm just going to show you what happens if I use 10 panels in a parallel and one in series, and how much hydrogen is produced through that. So you want to use, let's go to this output section, go to an online plotter and use this plotter. So we're going to connect this, okay? What's going on? Yep. So you're going to connect this hydrogen production rate to your left axis, because the hydrogen is not being produced that much. So it's, let's say 1,000 is a lot. We're going to change that to 10. And remember, the output unit system that has been configured for this hydrogen production rate is cubic meters over an hour. So we're just going to run this. And as you can see, 10 parallel modules of a solar panel with one in series would create this much. Let me run that one more time. Would create about 0 to 2 cubic meters over an hour of hydrogen throughout the year, from 0 to 8,760. So let's see what we could do right now. Now we want to convert this pretty much unit system to kilograms per day. So the first thing we could do, we could convert it to kilograms per hours. So how do we do that? You're going to use first an integrator to determine the total, let's say, the total amount of hydrogen that has been produced throughout the year. So you would come to this integrator and you would use this quantity integrator. So you're just going to import it here, and you will link link your electrolyzer to your integrator and the hydrogen production rate to it, right? And you could change the aesthetics of this by changing however you want it to be. And what you want to do right now is you want to add an equation. This equation will help you to see what is the input for your hydrogen production. So I'm going to use HP, which stands for hydrogen production, using the integrator, and I would create this link between the integrator and the equation that I have chosen. And now I'm gonna, put the link in the description where you could visit this website. This is a very good website that would read the hydrogen physical properties for you. So it's an online calculator. So what you do, as I told you, remember those two parameters, which are the temperature and the pressure. You would just input these values in here, and you would get, if you hit calculate here, you would get this density. So one thing that you're able to convert cubic meters to kilogram is using the density. So it's a good conversion in order to determine your hydrogen production rate. So this something will be implemented into the equation that you have here. So what you want to do is that you want to create an output, which is your daily generation, right? And the daily generation is equal to HP, the hydrogen production, times this value that we have read here, 0.5282, divided by 365, because we want to convert that into an average value per day. So TRNSYS is giving you pretty much from 0 to 8,760, but you want that to be in one day. So that's why you divide it by 365. So now that you've done this, you're going to add a printer that would help a lot in order to see what changes have been made in your assessments. So you're going to add this, but before that, you have to check something, right? The thing that we have to play with is the number of modules in series. That's why the default value was 1, right? We had this previously. What you want to do right now is change this modules in series depending on the problem that you have stated. Now, the best number in order to produce 5 kilograms of hydrogen per day in an average basis, for me was between 35 modules in series to 45. So I chose 40 as a good number in between. And you can also change the module area, but I set it as default. So that was the case here. So I'm just gonna change these integrator. So I think I spelled it wrong. Yeah, integrator. Yes. The equation will be set as the equation. This is going to be the hydrogen production. This is the printer, and this one is the plot. So let's run this and see what happens now. So pretty much we're able to see the difference here. And if I click on the printer and hit the edit in order to see how things change, you would see that, okay, right now, with this daily generation, it would give you this time, and the daily generation, if you scroll down to the end part, you will see that I have created about 5 kilograms of hydrogen in one day. Now you would see that here is written 8,760 because it's the default value for the printer of TRNSYS. But what we have done, we have divided it by 365. So it's just pretty much showing it in one day. And you can see that we have created about 5 kilograms of hydrogen. So the first part is understandable right now, and we can move to the next part where we would add a compressor in order to compress the hydrogen to 200 or 350 bars and store that hydrogen inside a storage tank in order to use that for our fuel cell, which we will talk further ahead. So we're going to just add this as part A. So this is going to be part A of our project. So we have determined the basic foundations of this study for San Francisco. So moving on to the next part, I just copied the main components that I want to add in order to link them to my storage tank, where the compressor will be used to increase the pressure of the hydrogen that has been produced, and we're going to store that in a vessel, in a high pressure vessel. So you can just like select the components that you want, click Control C and Control V in order to paste them again. So in here, we're going to just write down part B. This is important because it's going to give you a good view on what you're trying to do. So you're just going to have part B here. So now what we want to do is we want to add something as a compressor. So you're going to use a hydrogen system, use a compressor, and you're going to add this compressor to your workspace. Now you're going to connect your electrolyzer to your compressor. Now a compressor, before like linking them, I just wanted to say that the first thing is you don't want to change the compressor. This is a 3-stage compressor. It's pretty relevant because you're increasing the pressure from 7 bars to 200 bars. So the gas inlet pressure should change to 7 because the exit pressure is 7 from the electrolyzer, and you want your compressor to operate full time. But the main thing that you want to link is the volumetric flow rate. So you're just going to come here, and the hydrogen production rate will be connected to the volumetric flow rate. And if and the aesthetic parts of these linkages that you can see, I've changed them. You can just press right click on the links, properties, and change their style. So you can change it like to blue, hit apply. So it's not a big deal. And you can now plot to see like how will the production rate change. So you can add a plotter, for instance, in order to check things. So how much will it affect the production rate? It won't do anything much. So the volumetric outlet flow is the thing that we want to check here. So we're going to hit OK. When we hit OK, we want to come to this part. Sorry. I'm going to change this, like for instance, to 20 or 10. Yeah, let's just keep it to 10. So you would see that not a big change would happen. So this is the first one, which was related to part A. In order to see part B, you come here to graph 1. See if there's no change in it. You've done nothing but increasing the pretty much pressure. So the volumetric flow won't change at all. So you're going to copy this style as well. You can apply it to this as well. So now we want to add this hydrogen that has increased in pressure and store it in our storage tank. You would still come to this compressed gas storage. You are going to use a real gas for the hydrogen storage tank, and you're going to connect your compressor to your hydrogen storage tank. So the volumetric outlet flow will enter the tank. So you're going to link that here. And the things that you have to change. Now, there's one thing that you have to understand. You know that we have assessed and we've constrained the tank's volume to 370 cubic meters. But this is where you can change and play with it. It's just like the solar panels, where you can play with the number of modules in series. You have to see what is the best and optimum maximum pressure that your gas storage tank has in order to not face any sort of errors while running the simulation. So the one that I found was I think 350 bars, and you don't want to change anything else. And you have to also link you have to have this mediator as well between your hydrogen storage tank with the SOC of your tank. That's why we're sorry, you have to connect the pressure level to your tank SOC. So I'm going to also apply this color. So this will be the whole sector of the controller. So basically we've done this. We can also change that here. And now we can use pretty much a good style of understanding. So now I want to see that how much hydrogen can I produce in one day. So we're just going to add the same integrator that we had. So we will come to the utility section, the integrator, a quantity integrator, and we're going to add this here. So this will connect to this part, and the volumetric outlet flow will be connected to this. And pretty much what we want to do is we're going to also apply the style for this color. And now the same thing would happen just as part A, where we would add this, equation. I'm going to add it the new, say, let's name it new hydrogen production. And this will be the new daily generation. So this will be the new hydrogen production times the website that I showed you. You're just going to come back. You're going to apply 353 Kelvin, 50 degrees Celsius. But now this time your pressure has increased. 200 bars is equivalent to 197.39 atmospheres. And I just wanted to make sure things are on the right side. Now, if you press calculate densities now, this number, this value will be your density. So your density is increased from the previous time. So you're going to divide that by 365 and you would get a good linkage. And we'll see what happens to the hydrogen. Of course, it will tend to increase, which we expect, because the denominator, the numerator has increased as well. And then you're going to add your printer. So you're going to add this printer here, which would help you see what happens to your new daily hydrogen production. And I'm just gonna check things. So we could also change the aesthetic parts, apply style. So let's run this with the new variations of understanding. So we're just gonna let this run and see how much hydrogen that we have produced. So we're just gonna come to this printer section, click on edit, and you would see that this time we have produced about 130 kilograms per day. So when you increase the pressure, you have this much hydrogen in hand. Now you cannot, supply this hydrogen to any system. So what you're going to do is you're going to use this storage tank to store that amount of hydrogen for future time to use it. So that's why we're using this hydrogen storage tank. Then in the next section, which will be the next part of the video, we're going to discuss that how we're able to extract this hydrogen and supply it or feed it to our fuel cell in order to provide that electricity required for the absorption chiller system. So this part has also been finished. I hope that it was useful for you guys, but before that, let's do one more thing. Let's also see how the polarization curve of an electrolyzer works. So I'm just going to copy this. So I would also like to name this part C in order for you to have a better understanding of how to plot the polarization curve for an electrolyzer. So you're just going to click paste. I just copied this electrolyzer into a new one. So it will give you all the same values for each parameter. You want to use something known as an equation. So you're going to apply this equation. You're going to say current is equal to time times 0.1. So you want your current, it starts from any number, right? Your current starts from any number, like we'll see, from 100 amperes. And you're dividing it by 10 or multiplying it by 0.1. And this will decrease the value of your current throughout time until it reaches a value of 0. So you're going to
link this to your current, right? You're going to link this to your current, and you're going to use a plotter to see how things change. So I would use this plotter. I would give this the voltage that has been improvised from it. So we linked this voltage here, and we're gonna set this, because it's on the left axis, we're gonna give it, like, let's say 50. But there is one thing that you will have to understand. This is the stack voltage. It includes that 20 number of series and 3 in parallel. If you want the cell voltage, you have to link this to the left side. So if you run this and you come to this section, you're able to see that polarization curve that I showed you in the previous section. So let's just increase the value of this left axis to like 80 or 100, let's say. And you're able to see that the polarization curve has been displayed as well. And it tends to increase, for instance, to a stack voltage. So the left axis is your pretty much voltage. You can change that, as I mentioned before here, voltage. So it's going to be volts. And you can just, delete this or erase it because you don't need it at all. So once again, if you click run, you'd see that you have this voltage on the left axis, and the time represents your current. But the most important thing you have to always consider is that TRNSYS does not consider the concentration loss. So you're able to see this activation loss here, the ohmic loss, but you won't see that concentration loss that we want, that it would just go gradually increase upwards. So this is it for the total assignment of the electrolyzer. Hope it was helpful, and I'll see you in the next video where we would implement the usage of the fuel cell and a boiler system in order to supply the need and demand of thermal heat for the absorption chiller system. Take care, guys. Hope this video was helpful. Make sure to subscribe to this YouTube channel as well.